We are all engineering students at the Georgia Institute of Technology, located in Atlanta, Georgia.
The College of Engineering at Georgia Tech is ranked in the top 10 of engineering schools in the world.
We are all currently enrolled in the ME 1770 Engineering Graphics and Design course with the College of Engineering.
This class is focused on the design process of engineering. The fundamentals of this class are identifying features and geometric primitives of designs.
In this class, we both used hand sketching and computer-aided design software called Autodesk Inventor to model and design parts and objects.
Our instructor for this class was Dr. Akash Dikshit. Dr. Dikshit is a distinguished graduate of both the National Institute of India and Georgia Institute of Technology. Prior to becoming a faculty member at Georgia Tech, Dr. Dikshit worked in several companies that focus on computer-aided design, including SolidWorks, Geometric Software Solutions, and Differential Solutions. Using this background in computer-aided design, Dr. Dikshit teaches the ME 1770 course at Georgia Tech, where he shares his wisdom in computer-aided design with aspiring engineering students. Along with teaching this course, Dr. Dikshit conducts research in civil engineering applications. He has been published in the Journal of Applied Mechanics, Mechanical Research Communications, International Journal of Solids and Structures, and Journal of Intelligent Materials and Structures. Most notably, he was awarded the 2013-2014 ERAU Worldwide Research Award.
In the beginning, we were tasked with designing a new Mario Kart. First, we were assigned to this group based on our interests, and then we had to collaborate to brainstorm and come up with design process for our project. Following our plan, we created a team proposal listing our responsibilities among members of each section of the class, and how we were going to improve on the car that was used last year. After we had a solid landscape to work from, we were able to create isometric and multi-view sketches of our assigned parts. After that, we were able to use the Inventor software to its full capabilities in modeling those specific parts and modifying or upgrading them to fit the car's needs. These parts were compiled into assemblies. Then we were able to use the Inventor Studio to render images and create animations of the car and how the individual parts were assembled and how they would also function. For presentation purposes, we were able to create the presentation files that showed how the exploded views were compiled together to form an assembly, and the section views to show how the parts were inside of an assembly that were not visible from the outside. These views were projected onto a drawing file that has the ability to display the part names, the material of that part, and the balloons that indicate where each part is located. For the final presentation, we rounded out the project with this video to display the hard work and dedication that each and every group member has put into this project.
We're Group 6, Section C, and we are in charge of designing the engine, the seat, and the steering for the Mario Kart. I was in charge of designing the engine internals, which include the crankshaft, the camshaft, the valves, the pistons, and the piston rods. All the internal parts were fabricated from steel because of the high temperature environments. The pistons are designed to be relatively large in order to maximize the power output of the engine. And the crankshaft and piston rods are designed to have a very long stroke, or the overall distance the cylinder moves up and down in one cycle of the engine.
I was in charge of the engine exterior. The engine exterior are the engine oil pan, engine block, engine head, engine valve cover, and the engine coolant fan. Everything except for the fan is made from aluminum for its lightweight and durable properties. The fan is made from a lightweight but high temperature plastic. Weight in an F1 car is crucial in order to achieve the acceleration at its maximum peak. The engine exterior was designed to all bolt together as shown in order for easy repairability for the parts inside.
I was in charge of the seat and the harness. The seat is designed for ergonomics and based primarily on the design of an F1 style car. There's an integrated 5-point harness to ensure the safety of the driver. The seat is designed to be positioned so that it's tilted backwards in order to reduce the overall aerodynamic drag, yet to maintain the driver's line of sight. The seat is made of lightweight plastic material to reduce weight and cost. The safety harness straps are made of nylon, and the buckle is made of steel to make the harness as strong as possible.
I was in charge of designing the upper steering. The upper steering consists of the steering wheel, steering shaft, shaft housing, and the pinion gear. The steering wheel is designed for the driver's comfort and is modeled after a Formula One style steering wheel to improve the driver's experience. The steering shaft and steering shaft housing that connects the steering wheel to the steering rack are made from aluminum 6061, which is a lightweight yet extremely strong aluminum alloy used in the aircraft industry. The steering shaft connects to the steering rack, which turns the wheels with the pinion gear.
I was in charge of the lower steering, which consists of the rod, rack housing, the back housing plate, and the tie rod ends. The lower steering components are also fabricated from aluminum 6061 for, again, its lightweight and durability. The steering geometry was altered to allow for a tighter turning radius. Essentially, the outside wheel turns at a larger radius than the inside wheel to allow this increase in turning radius of the car.
Hi, I'm Jesse Simpson. I worked on the wheels and tires for the car as well as the brake rotors and spindles. The main component of the wheels and tires are the rims. The tires mount onto the rims and provide traction and allow the car to move. The rims are a stylish feature to the car and allow the car's owner to express himself and show other people a little part of himself. Basically, they're a form of self-expression. The rotors are an integral part of the brake system which allow the car to stop quickly and safely. Without them, the car would never stop and the driver would be placed in extreme danger. The spindles act as a block that sits between the control arms, allowing them to compress to absorb bumps in the road and therefore are a very important part of the suspension. The brakes are what the wheels and brake rotors rotate on and need to be very strong and well designed to prevent them from melting and destroying the car and its owner.
My name is Matt Myers and I worked on the braking system for the car. The main component of the braking system is the brake caliper. The brake caliper uses 4 pistons to squeeze a pair of brake pads into the brake rotor, which ultimately slows the car. This added braking power ensures safety and improves performance of the Mario Kart. I also designed the main rear axle and bearings within the wheel assembly.
Hi, my name is Adi, and I focused on 2 major components of the kart, the suspension and the drivetrain. The previous group did not have a functioning suspension. I redesigned our suspension based on a Formula One style pushrod suspension. The advantage of this design is that the components are collapsed to allow airflow through the side scoops. Also, the design produces more downforce through turns to provide better handling. The rear suspension was also redesigned to a simple compression setup. The only major components are control arms to keep the wheels attached to the chassis and rear coil springs to provide constant downforce to the back wheels. Since our car is rear-wheel drive, the downforce on the back wheels is necessary. The previous group did not have a functioning transmission, which is not conducive to racing, as the transmission allows the car to travel at different speeds over the same engine output. In connection with the clutch, I designed a 5-speed gearbox based off the gearbox of a 1986 Porsche 911 Carrera RS. Because our car has a similar power-to-weight ratio and weight distribution characteristics as that model of the Porsche 911. On the next screen you can see the gear ratios.
Hi, I'm Ryan Stroh, and the car we modified had virtually no working transmission, so it was crucial for us to create a design that allowed the car to function. To begin, we started with the basics of creating a transmission by designing a clutch, a gearbox, and a differential. I designed the differential, which is where the gears for the transmission connect to the rear axle and drive shaft that turn to allow the car to move. Secondly, I planned the gearbox, which contains the clutch and connection to the gear shifter.
Hi, my name is Jin Hyuk Kim. I worked on creating the clutch of the car. The clutch design is what allows the driver of the car to switch between gears when driving. I created parts that connect to the differential gear as well. I worked with Ryan and created the parts that connect between the differential and the transmission. The output shaft had to be connected to the differential by some type of connection to transfer rotation. I designed the pins, connectors, and gears so that the transmission and differential could work.
I'm Venkatesh Chinakonda, and Section M's design centered around speed, aerodynamics, and efficiency. The project started as a go-kart, and we were supplied the task of improving design. We thought that one of the best ways to improve the design would be implementing changes to the body design. Because we were creating an F1 car, we had to modify the body parts. We also implemented new parts to maximize the power of the engine and enable the car to be the best that it could on the track.
Hi there, I'm Trent Keatley. One part I designed was the front wing of the F1 car. The go-kart designs we were supplied with had a front wing that would not fit on the car and was not sufficient to limit air drag. The new design used smooth edges with a sharp front made of carbon fiber to best push air past the car and make it aerodynamically sound while also being lightweight. Another part I designed was the air scoop. The previous go-kart didn't have an air scoop, so this part was created from scratch. It was designed to look and function like an air scoop that would be seen on a typical F1 car. The air scoop is designed to take in passing cool air and supply it to the engine to lower its temperature and increase the power of the engine. Finally, I modified the chassis of the car. It was modified to have a sleeker, more aerodynamically sound body that resembled a typical F1 car. The chassis was important in that it houses all the other parts of the car, so dimensioning it just right was essential in order to have all the other parts fit together nicely.
Hello, my name is Christopher Armstrong. I was responsible for designing the rear spoiler, side panels, and the majority of the presentation files. With a similar purpose to the front spoiler, the rear spoiler is designed to keep the go-kart on the ground at high speeds. Like most of the exterior parts, the spoiler is made of carbon fiber to maximize strength and minimize weight. The side panels were designed to aesthetically improve the go-kart as well as decreasing drag and torque on the go-kart. Being also made of durable and lightweight carbon fiber, these side panels also provide the important role of providing airflow to the engine parts. Finally, I was responsible for creating many of the explosion parts and drawing files, as well as the animation for this group, to help detail the parts in our assembly and visualize the project as a whole.
Hello, my name is Rehan Khan, and one of the main parts I was responsible for was the air intake. The old design was a box filter which consumes much less air than the cone filter. I redesigned a cold air intake with the cone filter and added a heat shield. The cone filter allows much more air to be filtered through the system, resulting in better fuel consumption for the overall system. The heat shield ensures that the cold air is always cold and the engine does not heat up all the air that's being fueled into the system. With this new modification, the car is much more fuel efficient, and on top of it all, it adds a little more power to the system. Another part I redesigned was the straight pipe exhaust, which was an upgrade from the old bent exhaust. The bends in the previous exhaust made it much more restrictive, and the airflow did not flow directly straight out to the muffler. The muffler goes at the end of the exhaust, which results in less harmful emissions into the air. Altogether, the cold air intake combined with the straight pipe exhaust makes the car much more fuel efficient and adds a lot more power to the overall system.
One of the first modifications I designed for the car was the turbocharger system. This included the turbo and its piping system. The addition of the turbo provided the engine with more power through forced induction rather than a naturally aspirated engine. Once Section D was done with their suspension assembly, I worked on assembling the rest of the car by constraining the body panel, seat, and the drivetrain to the chassis. The toughest part of this stage of the project was adjusting the parts to fit the chassis, since some parts were not in proportion to the rest of the car. However, once I finished tweaking the parts, we ended up with a very sleek and well-designed Formula One car.
Hello, we're Group 6, Section M of the ME1770 class, and one of the main softwares we used for this class was AutoCAD Inventor.
So Inventor is essentially design software used by engineers to create 3D parts that you can apply to the real world. There's plenty of different features that you can use in order to customize your part any way you want it. You can change the material, the appearance of it, while also creating it exactly how you imagine it. Rayhan, why don't you tell them about assemblies?
Well, if you have an item with many parts, one of the things you can do is go into assembly file. You can take each individual part, put it into the file, place it into there, and then you can constrain certain parts to make it look exactly how you want it. You can fit in every single part to every single constraint, every single angle you want, and that gives you your overall item. Why don't you tell them about the presentation?
One of the cool things you can do with an assembly is you can present it in a multitude of different files. Your basic presentation file just shows you a multi-view sketch of any of your parts or assemblies. One of the really cool things you can do with Inventor is you can animate your assembly. You can make your assembly move through space, put itself together, or fade into existence.
Do you have anything to add to that?
And there's another view of Inventor, which are explosions, which literally explode your assemblies and show how each part is assembled. There's also another aspect which lists the parts, which are the parts list, and show where each part belongs in the assembly and how they're assembled.
This project was a learning experience for our entire group. With the engine internals, the process was very useful for me because it helped improve my knowledge of how engines work and function. It was very difficult to design engine internals that were both functional and practical.
During the process of the engine externals, I was able to figure out the importance of group communication and group management. In future designs, I would like to improve engine exterior to have cooling fans in order to help keep the engine cool so that it does not overheat.
While designing the upper area of the steering, I learned a lot in this project about the design and functionality of race cars. We had to research how steering systems are designed in Formula One style race cars, and this was a learning experience for me.
I was in charge of design of lower steering, and this project was very useful for me because it helped me refine my design and engineering skills that would be crucial for my success in my future career.
This project had helped me learn the design process and what it takes to create different parts in the real world. I enjoyed being able to use creativity to design different parts. I would like to continue to improve my design capabilities and learn more about all the features of Inventor.
This experience was a great learning opportunity. In this class, I had the opportunity to work on a long-term project with a group of like-minded individuals.
This is a project that I will remember for the rest of my life. I really enjoyed the concept of creating, designing, and improving a go-kart using the Inventor software. Cars and engines have been my passion for a very long time, and this allowed me to share all my knowledge and vice versa with other group members and groups.
This project will probably be one of the most memorable projects in my college career. I really enjoyed working on constructing a Formula One car, as well as working with my group members who were able to combine their skills and creativity to produce a successful Formula One car.
I would like to add more intake and exhaust valves to the engine in future designs, because more valves allows for quicker exchange of intake and exhaust gases, making the overall power output of the engine larger.
Being in charge of the seat, this project was very eye-opening for me because it helped me understand the design process that most companies undergo to design the components for an actual F1 seat. I would like to improve the design of the seat bubble by making it more detailed and adding working internals so that it would actually function. Also, I would like to add a platform to the bottom of the seat, allowing the driver to move the seat back and forth.
In future designs, I would like to fabricate the steering wheel handles out of soft rubber to increase the comfort for the driver.
In the future design, I would like to improve the simplicity of design in order to improve functionality and decrease the cost of production.
Things I would improve would be to definitely increase the amount of panels, as well as making the go-kart a little more aerodynamic overall.
My advice to the next generation of students would be to start early on your project and don't procrastinate. It can be very time consuming, so make sure you work hard on it early.
For any future groups out there, I would definitely recommend creating and maintaining a healthy and active communication, not only among your group mates, but also the members of the other groups in other classes.
One thing I would advise for future changes are to update the turbo system. There were a few parts that didn't make it into the system, such as the intercooler and all the pipes that go along with it. For future groups, I would recommend having more frequent meetings and keeping everything up to date. Remember, communication was the key factor in this whole project. One thing I would advise is to keep a lot of communication with your group, your partners, and the overall sections.
One of the most important aspects of this project is communication, which I believe that future groups should really keep as a priority and meet up weekly to stay on top of things. Communication will help everyone in the group keep up to date and be aware of what's going on and eliminate any assembly and constraining issues towards the end of the project. With that said, this project was something that I really enjoyed and believe that all of us worked really hard to produce something that we can be proud of.